Okay, so this is how we define what we call combustion analysis. Combustion analysis, this is just an analysis, or this is the analysis that is used to determine a chemical formula of a substance that contains hydrogen and carbon only, or maybe that contains hydrogen and carbon. This concept, or rather this definition, is very, very important. Okay, so we have to move a step forward. Mainly, we have to understand how to come up with the same chemical formula of every substance. So if you tried to go through the first document which I gave you, I explained very well in terms of how someone can even find the so-called empirical formula of a given substance. How to find the empirical formula of a given substance. So in this case, what you're going to understand, if we say combustion analysis, by the way, I remember at my grade 12, I learned something from organic chemistry, whereby we had this type of a process that can be used when it comes to breaking down of a large hydrocarbon into smaller ones. So the breaking of large hydrocarbon into smaller ones, we had different methods. We had analytical method. Yeah, we also had combustion analysis, the same combustion analysis. We also had what we call cracking method. So definitely here, I'm going to focus on combustion analysis because it also relates to organic chemistry. So how is this same concept related to organic chemistry, and how are we supposed to handle a lot of questions that concerns this same topic? This topic is very simple in chemistry. Like the simplest topic in chemistry is this one, including limiting reactants and percentage yields. So how do we handle questions on this one, and what are the steps that we are going to be taking whenever we want to find an empirical formula of a given substance using combustion analysis? At our grade 12, we learned about incomplete and complete combustion. I understand that some of you didn't finish the same to my topics. You just wrote your grade 12 without finishing the syllabus and the like. But here, things are very simple and straightforward. Fortunately, CBU is one of the best universities. We have two types of combustions. We can have complete combustion and incomplete combustion. Definitely here, we are going to focus mainly on complete combustion. What are the differences between complete combustion as well as incomplete combustion? So the only difference which is there between meaning complete combustion and incomplete is that if you use complete combustion, you are going to get substances such as water and carbon dioxide. But if you say incomplete combustion, this definitely means that you are lacking a certain amount of oxygen. Oxygen is not excess. Hence, in the case whereby oxygen is not excess, definitely you are going to get a minimal amount of carbon dioxide. Water is going to be complete, but carbon dioxide won't be produced. Hence, you are going to produce carbon monoxide. So here, I'll just focus myself on what we call complete combustion. So I know that some people are still wondering to say, what is this? Complete combustion, in simple terms, it is a type of combustion whereby an excess amount of oxygen is being used to combust a given substance or a given hydrocarbon. Hydrocarbons can be written as follows. You know that if you say hydrocarbon, that is a compound which comprises of carbon and hydrogen only. So it can be something like this. You can have a subscript here as X. You can also have something like this, subscript Y. If you combust this with a certain amount of oxygen in a complete way, you have to expect to produce what we call water plus carbon dioxide. So these are what we call the products, and we are going to focus on these same products whenever it comes to calculating for empirical formula. Because these, if I combine these, I have to get a certain substance here that is going to be made up of carbon, hydrogen, as well as oxygen. Okay, so we understand that this part, we are having two different elements. We have two different elements, which is carbon as well as oxygen. And also here we have hydrogen and also oxygen. How many atoms of oxygen do we have here? We have two different atoms. How many atoms of oxygen do we have here? We have two atoms of what? Of oxygen. So if the question comes to you using combustion analysis, how do they phrase a question? They'll just tell you to say a sample blah 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 combusted a sample of mass blah 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 combusted and produced this amount of water and this amount of what? Carbon dioxide. Then they will tell you to say, can you find the empirical formula? How do we calculate questions based on the same combustion analysis using the same procedure I'm going to show you right now? So there are certain things that we are likely to know whenever it comes to calculating for empirical formula. What are those? I know that if this is reacting with that, this is going to have its own mass given. Sometimes they can even give you 2 grams of this one. So the 2 grams of this one can produce maybe, they will say 7 grams of what? Of water, and also 5 grams of carbon dioxide. So since I'm saying like combustion analysis, in my definition, I mentioned something like combustion. If they say combustion analysis, they mean a substance that is containing carbon and hydrogen is being combusted. So in this case, oxygen is combusting this one. Why? Because this is the only substance which contains carbon and hydrogen. Then this one combusts this. The meaning of combusting simply means you are breaking this one using what? A hot oxygen. So this amount of oxygen is in excess. Hence, it will produce two different substances once you combust this. We are going to have water as well as carbon dioxide. Now, a question can be phrased. We are saying for us to come up with the empirical formula automatically makes or maybe comprise of 2 or maybe 3 different elements that are separated with each element having its own mass. Now, in this case, we have this, that. Sorry, we have this, and also we're going to have what? Oxygen. How exactly is it going to be for us to know the mass of hydrogen in this compound once we combust it, and also the mass of carbon in that same compound? So before I do that, I have to make mention some of simple ways that you are likely to do to follow when it comes to calculating what we call an empirical formula. Right? Okay. So we have 3 different concepts, or rather 3 different procedures that we are going to be following whenever calculating for empirical formula. What are those? I'll start here. So I'll say the first thing which you are likely to do, suppose you've been given carbon, you also have hydrogen and also oxygen. They want you to come up with the empirical formula for these. If you have the mass of this, you have the mass of that, and also this one, wow, it becomes very simple for you to clearly find what we call the empirical formula. What are we supposed to do in this case? This is where now we have to use what we call ratios. You have to put this to show that you're dealing with the ratios. Even here, you do likewise. But what exactly does it take for you to combine these 3 given elements and come up with a single element? One, when calculating for empirical formula, what should always come into your mind is, first of all, if you have a mass of this, a mass of that, and a mass of this one, or if you haven't been given their masses, you need to find. If you find the masses for every element here, the first thing what you are going to do is this. These masses being found here are not the masses that are found on the periodic table for every element. By the way, the periodic table you are using at your secondary level is not the same one that you are using here. Here, the periodic table is quite twisted a bit. They added certain things. Yeah. And this is why now we are going to be understanding why a lot of elements on the periodic table, they're not having their mass numbers as a whole number, like just a solid number without having my decimal places. You'll find that every element here is having a decimal place. Why? I mentioned that in the first document. If you didn't go through, try by all means to go through the first document. You'll be able to understand why we are saying every element must be having a decimal point. There is a reason which I gave there. Okay, So what are the procedures we are likely to follow whenever we are calculating for what we call empirical formula? First of all, if I have the mass of this, that, and that one, then I'll say divide the masses given for each element by their respective molar mass to get the number of moles for each. My question is, who didn't learn about how to find the so-called the number of moles? How do you calculate the number of moles for a given substance, having been given the mass for that same substance? Maybe they say this mass of this substance reacts with blah 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 blah. What exactly can it take for you to calculate the number of moles for that same substance? How do you calculate the number of moles? Just respond quickly and then we can proceed. If you know how to calculate the number of moles, tell us the formula to proceed. Praise.
So we say number of moles is equal to mass over molar mass.
So number of moles has to be equal to, we say, mass of a given substance. If you are talking about oxygen, you put O down there and you say molar mass of oxygen. This is how we calculate the number of moles. Same applies even here. If you have been given the mass of this one already, to calculate for empirical formula, we are using what we call number of moles. How do you calculate the number of moles? Having been given the masses for each element, for you to find its number of moles, you must divide the same mass given by the mass which is what? Given on the periodic table. Same applies on this one. By the way, these are common elements that you shouldn't be having challenges to master their number of their masses. Like for this one, carbon, it is having 12.01. That is grams per mole. This one is having 1.008. Some people they say 1.1. 1.01 is also okay. Grams per mole. Oxygen is having the same mass you are using per secondary level, which is what? 16.0 grams per mole. These are simple to my masses that you are not even be supposed to having some challenges whenever you want to calculate, maybe for empirical formula that is made up of three different elements, like the way I've displayed them here. So first of all, you need to do what? Divide each element. Divide the masses given for each element by the masses on the periodic table, which is the molar mass. For each, you divide with respect to what? To the molar mass is given. If this one is having 2.5 grams, I will divide that same 2.5 grams by what? 12.01 grams. Same applies to this one. And also the last one. Then the second point that you have to do is then, I'll say, after dividing by the molar masses, sorry, to get the number of moles, comma, then divide again throughout by the smallest number of moles. So this statement is very simple, straightforward. If you get the number of moles for this, the number of moles for that, and also the number of moles for oxygen, what are you supposed to do next now? You have now to divide throughout by the smallest number of moles amongst themselves. You have to divide throughout by the smallest number of moles amongst themselves. If this one is having the smaller number of moles, automatically you are going to divide now. Starting from here, you divide by itself, divide here by the same number of moles for this. Even on this one, you do likewise. The third concept, or maybe the third point that we are supposed to follow is this. Okay. All right. So the third thing is you say the best rule to apply all the times is that, comma, in a case where you get a number with decimal points, comma, so I'll put something inside the word, the speech marks or inverted commas, whichever. I'll say do not round off any number with decimals between 0.2 to 0.8. This is chemistry, and this is the best rule that applies all the time. This is the best rule that applies all the times. The cases after you divide now throughout by the smallest number, then you'll find that you're going to get some of the numbers that are going to be having my decimal places. If you get any number which is having a decimal place between 0.2 to 0.8, do not round off that number. Do not round off that number. Hence, you have to multiply throughout. You multiply throughout all the numbers that you are going to get for each respective element. Remember, we're moving in the vertical way. Each element is going to have its own line of numbers. Same applies in the middle and also the last element. So you have to multiply throughout by a number or a factor to get a number with decimal points below 0.2 and above 0.8. If you multiply now by a given factor throughout and you get the results, or maybe you get the numbers that are going to be having my decimal points that is less than 0.2. What I mean if I say less than 0.2 is this. If you get, suppose you get something like this, there are cases whereby you can get 2.3. So this you can't round off. You have to multiply by a number which is going to make this decimal place be greater than what? 0.8. If the number now is having, if this decimal place is now above 0.8, you can round off. If you have a number like this, suppose you have a number like, how can I put it? Okay, if you get to receive a number which is going to have a decimal point below this, you can also round off that number now. Why? Because the range has dropped, and also on the other side, the range has been increased. So these are the simple concepts, or rather procedures, that you're going to be following whenever it comes to calculate for what we call empirical formula using combustion analysis, or the normal way of calculating for empirical formula. If you go in the first document, I even mentioned how to calculate the empirical formula given elements in percentage format and the like. If you haven't done that, please get back to the documents and you'll be able to understand. For the new members, don't even worry, because everything is going to be what? Everything is going to be done for you people. Okay, we proceed. So in the beginning of combustion analysis, I just gave you a simple illustration to say how do we calculate the masses for every compound, for elements that are in a form of a compound. Suppose they give you maybe this same equation which I'm from writing, the one which made up of what's this? If you say Cx Hy, you combust this like this, you are producing carbon dioxide plus water. So my main aim is to make sure that I come up with oxygen, I come up with carbon in carbon dioxide and also hydrogen in water. Then the remaining amount now is going to be for what? For oxygen, or the remaining percentage is going to be for oxygen and the like. Now, how do we calculate the same masses for this one, which is for carbon, in where? In this. We have two different methods that are going to be using. Right now, I'll teach you the method which you can easily understand. For the chain link, you're going to learn this whenever you come on the campus. I can't teach you this because a good number of people are going to be getting confused. So, suppose you want to find the mass. If they say this sample is having 2 grams, right? They combust it and produce 5 grams for this and also 7 grams for that. Remember, combustion analysis deals with carbon, hydrogen. Then if there is another element which is being found in this case, is going to be what? Oxygen. Meaning that out of carbon dioxide, I have to find the mass of oxygen. From where? From this. And also here, I have to find the mass of hydrogen. From where? From this mass which was produced by what? By water, as what, in a form of water. How do we do that? First of all, you need to understand to say what is the percentage of carbon dioxide, carbon in carbon dioxide. You come also to this one, you say what is the percentage of what? Hydrogen in water. After you do that, you are going to use the same percentage by dividing it with what? By dividing it by 100, then you multiply by the mass given. Meaning that you are converting the same percentage of this in carbon dioxide in a form of grams. Okay, and how are we supposed to calculate that? We understand that in the second document, if I'm not mistaken, maybe in the first document, whichever, I even mentioned how to come up with the percentage composition, how to calculate the percentage composition for a specific element in a compound. Suppose you want to calculate the percentage of carbon from carbon dioxide, what are you supposed to do? First of all, you need to divide the element by the compound. Then you multiply by what? 100%. Meaning that you want to find the percentage of carbon in where? In carbon dioxide. After doing that, then you come to the issue of mass. The percentage you are going to get here now, you are going to divide it by 100 and you multiply by what? The mass. Meaning that you are converting the percentage of carbon in carbon dioxide in a form of mass. This is all what is going to be happening again to what? To hydrogen. So we start. I also say comma. Hydrogen. If you check hydrogen, you have two different moles, or maybe you have two hydrogen atoms in that case. I would say 2, because there are 2 hydrogen atoms in that case. You divide this by what? By the mass of water. You multiply by 100%. Okay, so by the way, don't even trouble yourself, because the percentage of carbon in carbon dioxide is constant. It is not changing. Even if they twist the equation, still you are going to get the same percentage of what? Carbon. But you have to show. Because if the question is saying 12 marks, you can't just go direct, since you know the percentage of carbon in carbon dioxide, then you calculate it direct. No. Show that, or you have to calculate to say carbon, you divide it by that, you are finding the percentage composition of carbon in where? Carbon dioxide. After doing that, now you come to the next thing, which is what? What is the number of the mass of carbon on the periodic table? That's right. It is very simple for you to easily understand. The mass number of carbon on the periodic table, it has to be, so I'll just list down the elements here. Carbon is having a mass of 12.01. Hydrogen is having a mass of 1.01. Then I'll say oxygen is having a mass of 16.01. I'll say chlorine is having a mass of 35.45. Aluminium is having a mass of 26.98. We also have nitrogen is having a mass of 14.01. Definitely, if you can continue, whichever you're going to find that potassium is having a mass of 22.99, and the like. Copper is having a mass of 55.85. Iron and the like, all those to my simple stuff, you can understand them and even master those to my numbers. So we continue, meaning that the mass of oxygen which is given here is the one which is going to be where on top. So for you to find the mass of this compound, I think you learned about this Kama-Eustace method that you used to do, or that you used to have a secondary level, whereby they say, if you were taught by a madam, you can even hear it say, so what we are going to do is this. You say carbon dioxide, then you separate this like this. You say 2 multiplied by the mass of oxygen. You come to carbon. Since we have 1, you say 1 multiplied by 12.01. Then you find the total. What answer are we getting? Okay, so we are going to calculate it like that. So I'll say, this is my calculator. I'm using the same calculator. I don't like expensive calculators because they just deplete financial statuses. So we're going to say here, how many carbons do we have? 1. I'll say 12.01. I'll say plus K. So we're going to have 2 multiplied by 16, like this. So if you say equal to, we are getting 44.01. That becomes the mass of carbon. You can say 44.01. That is grams per mole. Okay, you go to the number of mass for water, which is H2O. We are going to have 16 multiplied by 1. Here we are going to have 2 multiplied by 1.01. This is going to be 16 plus 2.02. You're going to get 18.02. This becomes the mass of water. I'll just put this kind of thing on top a bit. You proceed, Bane. You come to carbon. You say 12.01 over the molar mass for carbon dioxide we are from finding is 44.01. You say multiply this by 100%. You come here, I think this is going to be 2. You multiply this by 0.1 because we are having 2 atoms of hydrogen. You divide by its number of molar mass, which is 18.02 multiplied by 100%. We are trying to calculate for the percentage of every element in each compound produced, so that we can use the same percentage of it to find the mass. How are we going to find the mass? I'll keep on repeating this. After finding the percentage of carbon in carbon dioxide, I'll use the same percentage by dividing it by what? 100. Then you multiply with this mass. You're going to understand that it will give you the exact mass of carbon in carbon dioxide. Simple mathematics, we are able to follow. So the calculator here is helpful. You have to say 12.01 by 44.01. If you say equal to, then this answer you multiply it by what? By 100. What answer are we going to get? We are getting 22.3%. So carbon is equal to 27.3%. This is the percentage of carbon in carbon dioxide. You come to this one. If you multiply this by that, Ruben, why are you late?
very low.
Your phone, the battery is very low.
I was very low, at least.
Okay, okay. Don't worry because I'm trying to record everything which is happening so you'll be able to watch the video and connect from where we are right now. Okay, so if you see
All
on
right,
top here,
starting.
okay, if you check on top here, you're going to understand that if you multiply this by that, you're going to get what? 2.02. Then simple mathematics here, you just say 2.02, you divide this by what? By 18.02. Then you tell them to say equal to, we are getting, I think we've forgotten one thing because we're supposed to say 0, 2 if I'm not mistaken. Yes. And the answer, if you multiply here by 100, what answer are we going to get? Automatically, the answer is found to be 11.2. So hydrogen, the percentage of hydrogen in water is 11.2. These are constant numbers. Wherever you're going to go, this still remains the same percentage of what? Hydrogen in water. I'm illustrating this to you people so that you can easily understand what you are going to do in the example I'll give you. All right. So these are percentages that are constant for every element in where? In water, carbon dioxide, whichever. These numbers are constant. They're not changing. They are constant. So now for you to find the mass of carbon and hydrogen, I'll use these respective what? Percentages. I'm going to use these respective percentages to find the mass of each element, which is carbon as well as the hydrogen. Once you do that now, meaning that the mass that is going to remain will be the mass of what? Oxygen. How would you find the mass of oxygen? Suppose you have been given 2 grams for this sample. For you to come up with the mass of oxygen, I'll say after finding the mass of carbon using this percentage and also the mass of water using this percentage in their respective compounds that are produced, automatically I need to add the mass of this that I'm going to get and also that one and subtract from where? From the original sample. What I mean is this. Okay, I put it like this. What I mean is this. Okay, forget about this part first of all, because you end up getting confused. Let me do like this so that people can just concentrate on this part. So what you're going to understand is this now. But let me do this. It's kind of confused, guys. My people. Okay. Okay. So we have carbon, which is equal to 27.3%. We have hydrogen, which is equal to 11.2%. How do you get the mass for this one from carbon dioxide? I would say 27.3% of this carbon, you divide this by what? By 100% now and multiply by the mass of carbon dioxide, which is 5 grams. You do likewise to this one. I'll say 11.2% of this, divide this by 100%. You multiply this by what? By 7 grams that is given on the page, on the other page. So here the understanding will be like this now. The mass I'm going to get here and the mass I'm going to get there will be the respective masses for what? For each element. So here I'll say what will be the mass here that I'm going to get if I do the mathematics. You are going to understand that I'll say 27.3, you divide this by 100 equal to, okay, we are getting that. You multiply this by what? By 5. What answer are we going to get? Automatically, we are getting the mass of carbon as 1.365. By the way, in chemistry, it's better you leave your answers to at least 3 decimal places. So this is going to be the mass of carbon has been given as what? 1.365. I'm giving you this as the example, not what, I mean, as a simple illustration that we are going to use when it comes to calculating for an example, if you want to deal with the example. So this becomes the mass of what? Carbon. You do likewise to this part again. You come here and you say, uh, say 11.2. You divide this by 100%. We are getting that. Then you multiply this by 7. What answer are you going to get? So definitely here we are getting the mass of hydrogen as 0.784 grams. Now, to get the mass of oxygen which is remaining, what are you supposed to do? You say oxygen has to be equal to the total mass of a sample minus the total mass of hydrogen and carbon dioxide. So if we have that 2 grams for the sample, we say O has to be equal to, you say 2 minus, open bracket, you're going to say 1.365 plus 0.784. So I know sometimes they can, but they can't give you this number to be a number which is less than what you're going to get here after adding. So if we add this number which is here, I'll say plus 1.365. What answer are you going to get? Here we are getting a very big number, meaning that our approximation here was quite good, since we are just giving a simple explanation for us to easily understand. But they can't give you this number which is going to be less than the numbers that you're going to get here after calculating. So suppose even you change this one to be 3, then we have the total number here as what? 2.149. Then you are going to say 3 minus the answer. Definitely 0.851 is going to be what? The mass of oxygen, which is 0.851. This is how you do calculate the masses for every substance, or rather for every element. Now, having gotten these numbers now, what are you supposed to do if you've gotten those simple numbers, or maybe we say the masses for every element? What you're going to do next now is this. So I'll write it like this now. I'll say CHO. We have respective masses that we are from getting. For oxygen, we've gotten 0.851. For hydrogen, what mass did we get? We got 0.784, if I'm not mistaken. Okay. So for carbon dioxide, we got 1.365, if I'm not mistaken. Now, the first principle that I gave you, or the first point I said, these masses that you are from finding, to get the empirical formula, first of all, you have to divide with their respective masses. You have to get, you have to find their number of moles with respective masses, meaning that this one, I'll divide this by what? By its mass, which is 12.01. This one, I'll divide it by 1.01, and this one I'll divide it by what? 16. So if you come on your calculator, you find that we have the mass of oxygen, which is 0.851. You divide this by 16, and you write your answer here as follows. You say 0.05319. At least you leave it to 4 decimal places or significant figures. It makes sense. You come to the part which is in the middle. You do likewise by saying 0.784. You divide this by 1.01. What answer are we going to get? So here we are getting 0.7762 for this column. You come to the left hand side. You say 1.365. You divide this by 12.01. What answer are we getting? We are getting our answer as 0.11366. Then you look at the number which is less than every number. In this case, you are going to find that oxygen is less than what? Whichever number. The second point, we said you divide now throughout by the smallest number to get a whole number, not the number of moles. No. So here you say 0.05319. Here you say 0.05319. 0.05319, and also there you say 0.05319. I know someone from Chilawombwe can even do mathematics here by punching on the calculator. Say, okay, so as in if we say 0.05319 divide by 0.03519, what answer are we getting? Okay, you find that it gives a different answer due to the what? Due to the changes that we have. But if you divide this number like the way it is, you divide this by that one again, you're going to get what? You're going to get the exact answer as the 1. You come to this part now, you say this is going to be 0.77, you say 65. You divide this by 0.05, 0.05, that is 319. What answer are we going to get? We are getting 14.6. Then whenever you come on this part now, you say 0.11, that is 366. You divide this by 0.05319. What answer are you going to get? We are getting 2.1. So due to this number which is in the middle affects everything now. It affects the remaining what? The remaining numbers. How? It affects the remaining numbers in such a way that it is having a decimal point which is in the range of 0.2 to what? To 0.8. So meaning that you can't round off this, even if it is above 5. In chemistry, we don't round off like that. You have to make sure that here you're having a decimal place which is above 8 or below what? Below 2. So if we, for instance, we had two numbers like 2.1, 14.1, I would have just rounded off to what? To the same exact numbers. So here you have to look at a factor which is going to make this be or maybe have a decimal place which is greater than what? Which is maybe below this one and also above that one. So if you try to multiply by 2 throughout, what answer are you going to get here? You find that if you multiply by 2 throughout, you are going to affect again this one. This one can be stable, that you are going to affect what? This one. Hence, the best way of doing this is by multiplying by a factor which is going to make sure that you have a number which is less than this. Which is less than what? 2 a decimal point and also above this one. So this is how we do calculate what we call empirical formula, even if you have been given the combustion analysis. This is how we do calculate what we call the empirical formula given the combustion analysis process. Okay, so my example goes like this. Combustion of that same example which you are from writing, you can just leave it like the way it is. Don't rub it. It is going to apply on a certain concept that I prepared also. So combustion of 28.4 grams sample of organic compound containing carbon, hydrogen, and oxygen produces 54.3 grams of carbon dioxide and 15.6 grams of water, that is H2O. So they're saying find the empirical formula for the compound. Okay, so combustion of 28.4 grams of organic compound containing carbon, hydrogen, and oxygen produces 54.3 grams of carbon dioxide and 15.6 grams of water. So they're saying find the empirical formula for the compound. So here I won't even take time because what I'm from explaining, I think it is very clear and loud. I'll just go direct into solving the same question so that I can apply the last concept which I just introduced. So before you even start solving this question, you have to analyze what you have been asked for. So here we have say solutions. So we have data here. So my data here says I have a sample having 28 point. This sample, okay, is having 28.4 grams. We have carbon dioxide, which is having 58. That is sorry, 54.3 grams. We also have H2O, which is having 15.6 grams. So, if I'm to ask, what is the percentage of carbon in carbon dioxide? Quickly, the percentage of carbon in carbon dioxide. Just give me the answer. Then we can proceed. We are from finding those 27.3, right? So meaning that you are going to use the same percentage to find what? To find the mass of carbon in where? The mass of carbon in carbon dioxide. So say 27.3%, you divide this by 100%. You multiply by what? 54.3 grams. Now what answer are we going to get once we do it like that? Okay, so we have 27.3, divide this by 100, you say 54.3. Is it 54.3? Yes. So what answer are we going to get? Automatically, we are getting the mass as 14.8239. So meaning that carbon is going to have a mass of 14.8239 grams. You come to hydrogen, we are having 11.2% over 100%. You multiply this by the mass for water to get the what? The mass of hydrogen. So this is 15.6. So definitely we are having, okay, 11.2. You divide this by 100, multiply this by 15.6. What answer are we going to get? The answer is given as 1. Sorry. So we have 11.2, divide this by 100, multiply by 15.6. So we are getting the mass of hydrogen as 1.7472 grams. Now we have two different masses. What did I say about the issue of oxygen? How are we going to find the mass of oxygen now at this moment of time? How are we going to find the mass of oxygen at this given time? Quickly.
Total mass of a sample minus the total mass of hydrogen and carbon.
Okay. So I'll say oxygen has to be equal to the total mass of the sample in this case is what? 28. So you say 28 minus the sum of these two, which is going to be what? 14.8239 plus 1.7472. So here, definitely I'll say, okay, I'll say, sorry, I've forgotten to put 0.4 at this one, 0.4 minus, okay. So we are going to say 28.4 minus 14.8239 is 8239. You add this with 1.7472, you close. Oxygen has been found or has been given as 11.8289 grams. Now we have all the three masses for each element. Now what are we supposed to do next? So here I'm going to do it like this now. Just get a simple piece of paper. So I'll write it as follows. I'll say CHO. Okay, so what is the mass of carbon dioxide? We are saying the mass of carbon is what? 14.8239. Hydrogen is 1.7472. Oxygen, we've gotten 11.8289. Then you find the number of what? The number of moles for every element with respect to what? To each number of mass on the periodic table. You divide this one by each number of mass. I remember I gave you a simple gamma table which was showing the masses for every. Where is that gamma thing? Where is the gamma thing? Okay, it's okay. But this one, it has to have 12.01. This one is having 0.01. This one is having 16. So I'm going to come here. Remember, the number which is there already on the calculator is what? The mass for what? For oxygen. You divide this by 16. And we are getting 0. I'll round off this number to 4 significant figures. So I'll say 0.7393. You come in the middle, you say 1.7472. You divide this by 1.01. Fortunately, we are getting 1.7230. If you come to this other side, it is